So this week we're going over one sample t-tests, but first let's start with the warm-up. So take a few minutes to work through these warm-up problems, dealing with z-scores and confidence intervals, and then we will go over them in a minute. Okay, so for question 1, after it rains, you notice an abundance of slugs in your backyard. You measure the length of all the slugs in your backyard and assume that you've measured the entire population. So we're assuming that we've measured the entire population. According to the data, the average length of these slugs is about 6.7 millimeters. So that's our mu, population mean. And our standard deviation is 2.1. So our population standard deviation is 2.1. What proportion of slugs is greater than 7 millimeters? So our xi is 7, and we need to calculate a z-score for that value. So it's xi minus our mean divided by our standard deviation. We now need to calculate the proportion that is greater than 7 millimeters. If we draw this out, get our mean of 0, our z-score is very small, 0.1428. So a very, very small z-score. And we want to calculate the proportion to the right of that. Our table automatically gives us this value to the left though. So when we look up this tabled value, positive 0.1 and then across to 0.4, we get 0.5557. But that would be this area. We want the area to the right. So we need to do 1 minus 0.5557. And that's the proportion to the right, or the probability or the proportion of slugs greater than 7 millimeters. For B, what portion of slugs lies within 0.67 standard deviation units of the mean? So the mean is 0. We're looking for between negative and positive, excuse me, 0.67. So those are our two xi values, negative 0.67 and positive 0.67. Or actually, no, sorry, we actually don't have any xi values. We just have x or zi values because it's already in standard deviation units. Sorry, that is our population standard deviation. So that's the 2.1, and our population mean is 6.7. The proportion that we're looking at then is between 0.76 and negative 0.78 standard deviation units. This area between, which means we have to take the proportion for this value and subtract from it the proportion from this value, which corresponds to this area. So that's equal to, let's see, 0.6 across then to the 7, get 0.7486 minus, go to the negative version, negative 6.7, and we get 0.2514. So 0.4972, that's the proportion between these two z-scores. Question 2, the next year you remeasure all the slugs in your backyard. The data is shown below. You now assume this is not the entire population, so you don't know the population variance. Create a 90% confidence interval for this data set. Because we don't know population variance, we're going to use the t-distribution. First, let's calculate the average for our sample, the standard deviation for our sample, so .s. Our standard error is our standard deviation divided by the square root of our sample size Our sample size is just all of the samples we have. Our degrees of freedom is equal to our sample size minus 1. Our t-crit, we get that using the t.inv or t.inv.2t function. So t.inv, this is a two-tailed test, so I'm going to use the two-tailed version with a probability, a p-value of 0.1 because this is a 90% confidence interval. It'd be 0.05 if it was a 95% confidence interval. Next, we need to enter our degrees of freedom, and this gives us our critical value. We could also calculate this using the t.inv function, but our probability would be 0.097, or actually 95. Because the t.inv function, this, you have to kind of think of this alpha as if it was on a number line. We want alpha over 2 over here and alpha over 2 over here as well. If we actually think of this as a number line from 0 to 1, I know usually we think of the mean in the center, but we're thinking of this as an actual, this x-axis is a number line from 0 to 1. This alpha over 2 for the lower half below the mean of 0 would be negative. This would be our negative t-crit. Above the 0, we'd get a positive t-crit. At this point on the number line, our alpha would be 0.00. See this two-tailed, yeah, 0.025. All right, I guess if we're doing a 90% confidence interval, this would be 0.05. Over here, it would be at 0.95. So that we still get 5% here and 5% here. But our alpha values are associated with this negative or this positive version of t-crit. So if you use the t.inv function for these two-tailed equations, you have to remember this, that you can't put in 0.05 here. If I did, I would get a negative version of our t-crit, which is incorrect. Or it's not necessarily incorrect, but it's more challenging to do the rest of the calculations with. We'd have to account for that. So our confidence interval is our mean for the upper one, our mean plus our critical value times our standard error. For the lower one, it is our mean minus our critical value times our standard error. So this is the range for our 90% confidence interval. For B, if you assume this did represent an entire population and your population variance was 2.1 millimeters, how would your confidence interval change? Construct a 95% confidence interval, so alpha is equal to 0.05. Our mean is the same as before. It's still just the mean of this data set, so right there. Our standard deviation is the same. Or actually, sorry, our standard deviation we are assuming is the population variance, so it's 2.1. Our standard error, let's actually just fill in the sample size again. So our standard error is our standard deviation divided by the square root of our sample size. Our ZI, because now it's a population, we have population variance, which means that we can use a Z distribution. So our ZI is then calculated from the table that we have. We are looking for a ZI for a 95% confidence interval. We can calculate this doing actually the t.inv, just like we did with the t values, the t critical values. The only difference here, so we're going to say 0.097 0.975, actually 0.05, I forgot, we can use that with this two-tailed version. Our degrees of freedom, though, we're actually going to type a very, very high number. We're just going to type an arbitrarily high number to simulate having a huge sample size. Because remember, as our sample size increases, our t-distribution begins to converge on our z-distribution, which has a lower variance. So by having this sample size, this ridiculous sample size of 100,000, we're essentially simulating a z-distribution. Our upper confidence interval is then our mean plus our z-crit times our standard error. And our confidence interval lower is our x-bar minus our critical value times our standard error. Written as a range, that would be from 4.5 to 8 to 6.905. If this were a 90% confidence interval, we could do the same thing, except our zi and confidence intervals would change. So our zi would still use t dot I and b dot two-tailed. Our probability would be 0.1, and our degrees of freedom, again, would just be some arbitrarily huge number. And we'd get this as our new z critical value. Confidence limit for the upper would be our mean plus our critical value for 90% times our standard error. And the lower one would be our mean minus our critical value times the standard error. I used the wrong, yeah, there we go. Just wondering why that looked weird. There you go. So remember, our confidence interval is equal to our mean plus or minus our critical value, either t-crit or z, times our standard error. We use our z-crit when we know our when we have an unknown population variance, and our z-score, our z-crit, when we have a known population variance. So we're talking about the one sample t-test for hypotheses about a single mean this week. For hypothesis testing, we begin with a practical biological question. Maybe how does the population of, how does the size of males versus the size of females differ from each other, or do they differ at all? We may turn that then into a statistical question. Are the means different between these groups? We then do a formal statistical test and then come to a decision about the conclusion. So we're using these one sample t and z-tests to determine whether or not a treatment affects the mean response of samples. So we're comparing means and we're seeing if treatments affect them. We use a t-test if the population standard deviation is unknown, and a z-test if the standard deviation is known for the population. A null hypothesis, or H sub 0 or H naught, is a statement about a population trait usually predicting no difference or relationship. So in the previous example, if we're talking about the weights or sizes between males and females, our null hypothesis would probably be that there is no difference between males and females. Our alternative hypothesis, H sub A, is our statement about a population usually predicting a change or relationship. So an alternative hypothesis for the male and female example may be that that males are larger than females, or females are larger or way more than males. We then have our probability, or p-value, which is the probability of a result found in your research study occurring under the assumption that the null hypothesis is true. So assuming that your population mean and your sample mean are from the same population, they are the same thing, how likely, what's the probability of getting the value that you got from your data? And then we have our significance level, or alpha. And this is the cutoff value that researchers somewhat arbitrarily select and then use to decide when to reject the null hypothesis. It's usually 0.05. And we say that if our p-value is less than alpha, we reject the null hypothesis and accept the alternative hypothesis. So if our p-value is less than usually 0.05, we would accept the alternative hypothesis. We test our null hypothesis by comparing the means, or variances sometimes, of the treatment group and determining how many standard deviations the treatment group is away from the control group. And remember that these standard deviation units, how many standard deviations, is referring to our Z and T scores. This ZS and TS, S stands for sample, is sometimes represented as calc, and that's typically how I will refer to these, as T calc and Z calc. So the first thing you want to do is write out the hypotheses. So the null hypothesis is H naught. The alternative is H sub 0, or sub A, sorry. Mu is our unknown mean, and mu naught is our traditional mean response from our control. This is our population mean, or our null mean. For a two-tailed test, our null hypothesis is that our sample mean is equal to our population null mean. Our alternative is that they are not equal to each other. For a left-tailed test, our null mean is that our sample mean is greater than or equal to the null mean. Our alternative is that it is less than our null mean, which makes sense if we're talking about left tail, because we're talking about the left tail of a distribution. For a right-tailed test, our null hypothesis is that our mean is less than or equal to the null mean, and our alternative is that our mean is greater than the null mean, which again makes sense because we're looking at the right tail of the distribution. A two-tailed test is looking at both tails. The null hypothesis always has some type of equal sign, and both hypotheses combined must cover all possible outcomes. They must include the entire sampling space. Here are some examples of potential alternative hypotheses for two-tailed, left tail, and right tail. So for a two-tailed test, Does taking a medication change the mass of mice when taken over 6 weeks? This is non-directional. We are just asking, is our mean the same before and after? For a left-tailed test, when taking a heart medication, does blood pressure decrease over time? We're asking, is it smaller? We're looking at a directional change. And for right-tailed test, does the use of a phosphorus-rich fertilizer increase plant growth? So we're looking at the positive side. We're curious, does the treatment increase something? This is a right-tailed sample t-test. The next step would be to choose a significant level, or our alpha level. And this is, as I've said, is typically 0.05. And we reject the null hypothesis when our p-value, our probability value, calculated in Excel or R, is less than or equal to 0.05. We now want to find a critical value using our table or a computer. When we use a two-tailed test, we need the positive and negative versions of our t-crit for alpha over 2. When you look it up in the table, you'll look it up going to the correct degrees of freedom, and then over at the top, alpha over 2, so that we have 1/2 of alpha in each side of this distribution. When we have a left-tailed test, our critical value should be negative, and all of alpha is over in the left side. For our right-tailed test, our t-value, our t-crit should be positive, and again, alpha isn't split, it's entirely in one side. In some programs, we have to use this funky little minus alpha over 2. For example, in the t.inv function, we have to use this 1 minus alpha over 2 for two-tailed tests. It changes a little bit program and function to function. You just have to kind of get used to it, but if you ever need to double check, I have annotations about how to do that and what functions use which format in the New Functions tab on Excel. Okay, so looking at the t-distribution for a hypothetical sample with a sample size of 16, so 15 degrees of freedom, for a two-tailed test with alpha of 0.05, if we look that up on the table to 15, and then alpha of 0.05, but it's two-tailed, so we need to divide that by 2, we find that our critical value is 2.131, which we have here. But because this is two-tailed, we're talking about both the positive and the negative versions of that, with our mean of 0 in the center. If we got a t-calc, a calculated t-value that was less extreme, either less positive than this, so somewhere over here, or less negative than this value over here, so somewhere over here, we would fail to reject our null hypothesis. We would fall into this fail to reject region. So if our t-calc was, let's say, 1.8, we would fail to reject. On the other hand, if our t-calc was equal to 2.9, it'd fall into this rejection region, and we would reject our null hypothesis. Same if it was negative. If it was negative, like 4, we would reject our null hypothesis. It would fall into that rejection region. So we reject our null hypothesis when our test statistic is too far from the population mean, and this distance is too big. Next, we want to calculate our test statistic. And we do that, this equation should look pretty familiar. We have our mean minus our null mean, then divided by our standard error. Next, we compare the critical and calculated values. If the value of the test statistic falls in the rejection region, we reject the null hypothesis and accept the alternative. Otherwise, we accept the null hypothesis. So here's that depicted again. So for a two-tailed test, if our critical or our calculated value falls in this region, we do not reject. If it falls outside, either on the more negative or positive end, we reject our null hypothesis and accept the alternative. If we have a one-tailed test, either left or right-tailed, we can, if our t-calc falls within this region, even if it's way over here, a very, very extreme positive value, if we're only looking at the left tail, we don't care about that. We only care and will only reject the null hypothesis if our value falls in this region. Same for the right tail. If we get a calc value around here, or even in the very extreme left tail, we still do not reject the null hypothesis because we're asking about a positive change. We only care if it's over here. Next, we can obtain a p-value. In this chapter in the lab manual, there is a section on calculating or estimating p-values and getting a p-value range. We're not going to do that. We're going to be using Excel and R instead to calculate exact p-values. And we use this t.dis. There's a couple different versions that I will go over in a minute. This function will give us the probability of obtaining a test statistic as extreme or more extreme than the one calculated. And that's the actual definition of a p-value. So as extreme or more extreme, what we're referring to is this extreme kind of allows us to talk about both positive and negative ends. So if our t-calc is here, or t-crit is equal to, let's say, 1 and -1, a more extreme value just means more standard deviations away from the mean. So -2 would be more extreme. +2 would also be more extreme. And using this language of as extreme or more extreme is the reason why the reason why we do that is because it could be a negative or a positive value, and so it doesn't really make sense to say more positive or less positive or bigger or smaller or greater than or whatever. And that's why we use this extreme language. So our p-value is essentially the probability of a t-calc more positive or more negative than the one you calculated from the data, right? So either more negative or more positive. Next, we want to make a statistical and biological conclusion. Our statistical conclusion is whether or not we reject or fail to reject the null hypothesis. And then you give a reason why you make that conclusion. So compare the t-crit and t-calc and refer to a p-value. For the biological conclusion, you answer the original question. So why was this experiment run in the first place? And it's equivalent to the results or discussions tab. So an example, let's say for the pH for plant growth, we may find that our calculated value is more extreme than our critical value, and our p-value is less than 0.05, so we reject the null hypothesis and accept the alternative. That would be our statistical conclusion. Our biological conclusion may then be that adding fertilizer to the soil significantly changes the pH of the soil or the growth of the soil or the growth of the plants. So those are the kind of answers that I'm looking for when I ask you to give me statistical and biological conclusions. There are a couple different types of error that we encounter when we run tests like this. The type 1 error is the rejection of a true null hypothesis, also known as failure to reject. or I think these are actually backwards. This should be failure to accept. So failure to reject the null hypothesis. Or maybe I got that backwards. All right. Anyway, so type 1 error is the rejection of a true null hypothesis, and it's represented as alpha. So that's what our alpha value is. It's the probability of us making a type 1 error, the probability of us accidentally rejecting a true null hypothesis. Type 2 error is the acceptance of a false null hypothesis, and it's represented as beta, the probability of making a type 2 error. So here in this figure, we have the truth about the population. Either our null hypothesis is true or our alternative hypothesis is true. On the left, we have our decision. We can either reject the null hypothesis or accept the null hypothesis. Rejecting the null would just mean accepting the alternative, in which case this would be the correct decision. We want to accept the alternative because it is true. If we were to reject the null hypothesis, even though the null hypothesis was true, we'd be committing a type 1 error. If our alternative hypothesis is true, but we accept the null anyways, we've then committed a type 2 error. And these errors come just from anything really. They can be sampling error, they could just be variation in the population, they could be issues with equipment or sampling procedures. There is always, always, always possibility of error, no matter how careful you are with any experiment run. Okay, so on page 110, there's a worked example. And this is the same scenario as in the chapter 9 soil pH example. So the question at hand is, how does adding fertilizer change the soil pH? In the original question, we're worried about soil pH becoming too basic and there being an outbreak of nematodes that. So in this population, without fertilizer, the soil pH is 6.3. So our null mean is 6.3. We then ask, does the new fertilizer alter the pH? So is this a one-tailed or a two-tailed question? This is a two-tailed question. We're not asking a directional response. We're not saying, does it increase or decrease? We're just saying, does it change it? Is it different? If the fertilizer changes the average pH of the soil, then we may want to add another chemical to bring the pH back to 6.3. So that's the data. Those are the pHs for the samples. Our hypotheses is that our null hypothesis is that our sample mean is equal to the population mean of 6.3. The alternative is that it is not equal to 6.3. Last week, we calculated that the sample size is 20, the mean is 7.11, the standard deviation is 1.137, and the standard error is 0.254. Clearly, 7.11 is different from 6.3, but statistically, they may be the same number because of sampling error. If we take heights of women in Southern California as an example, maybe the average woman in Southern California is 5 feet 6 inches. If I randomly pull 7 women off the street and measure them though, I probably won't get that as my average every time, right? There's a little bit of variability. So essentially we're testing statistically to see if the variation in this data may compensate or cover this difference from 7.11 to 6.3. and that these samples are indeed from the same population, or that the treatment has no effect. So first, let's find our critical values. The decision point in determining whether the sample belongs to the population. So we need our degrees of freedom in alpha to find the critical value in the table or in Excel. So this is a one sample, two-tailed t-test. Our degrees of freedom is 19 since our sample size is 20. Alpha is 0.05. On questions on homework assignments and quizzes, exams, all that stuff, I will be giving you the alpha value, but it is, again, almost always 0.05. So here we have our table. Alpha over 2, so 0.25, 0.025. We have our degrees of freedom is 19. So our critical value is 2.093. Now we can calculate our t-calc. And it is our sample mean minus our population mean, or our null mean, divided by our standard error. So that's a representation of what we have so far. We have our critical values on the negative and positive side, and we have our calculated value, which falls in the rejection region. It is more extreme, it is further from the mean than our critical values. And just remember that these t-values and z-scores are standardized numbers for the original pH values. So if we were to look at these red numbers here, that's essentially what we're saying. The mean is 6.3 plus 2.093 standard deviations would be 6.73 minus 2.093 standard deviations would be 5.67. But our actual sample mean is 7.11, which is 3.58 standard deviation units from the mean. So we come to a statistical decision. Since our t-calc is greater than our t-crit, our p-value is less than 0.05, we reject the null hypothesis and accept the alternative. Biologically, that means that the soil pH is significantly different from 6.3. In this case, it is greater than 6.3 with the addition of the new fertilizer. We are now at risk of a nematode infestation. If the soil pH with the new fertilizer was actually 6.3, like maybe we take like 40 more samples and we find that the mean is actually 6.3, then the conclusion that we came to in this test would actually be incorrect, and we would have made a type 1 error. We would have rejected a true null hypothesis. On page 111, there's another example. Here we're considering a situation when we are testing the enzymatic potential of a newly discovered protein. The researcher hypothesizes that a 0.01 molar solution of the new protein will accelerate the degradation of a substrate, In the absence of catalysts or enzymes, an initially 1 molar solution of the substrate will remain at that concentration. The researcher makes 16 test tubes of 1 molar substrate and adds some of the new protein to create a 0.01 molar concentration of the possible enzyme. She then waits 8 hours and measures the concentration of the substrate to get the molarity values below. So, an enzyme speeds up reaction time. Therefore, if a protein is an enzyme, it would decrease the concentration of the original solution. So that's what we're looking for. We're looking for a decrease in the concentration. So a concentration less than 0.01, or sorry, 0.1. So let's calculate our mean, variance, and standard error and write down our hypotheses. This is a one-tailed left-tailed t-test. So our null hypothesis is that our mean, our sample mean, is greater than or equal to 1. That's the original molarity. Our alternative is that our mean is less than 1, less than the original molarity. Our concentration has decreased because our new protein is an enzyme and it's breaking down the concentration of the other protein. Our sample size is 16, our degrees of freedom is 15, our alpha is 0.05, and our critical value, T-crit, is negative 1.753, and that comes from the table. Right, if alpha is 0.05 and we don't have to divide it, our degrees of freedom is 15, then we get 1.753. It's negative though because this is a left-tailed test. We're looking over here. Our mean is 0.9875, our variance is 0.00098, and our standard error is 0.007826, so very small. So our t-calc is equal to the mean minus our null mean divided by our standard error. And we get our t-calc is negative 1.597, which is less extreme than our critical value, which means that our p-value is greater than 0.05. Again, as I mentioned, we're not calculating ranges, so don't even worry about this. All that matters is that our p-value is greater than 0.05. And that our concentration is not significantly different after the application of the tested protein, so we don't reject the null hypothesis, and this likely means that our new protein is not an enzyme. Here that is drawn out. So our mean is 1 molar. We then have our t-calc value and our t-critical value. If our t-calc had fallen in this rejection region, we would have rejected the null hypothesis, but it is less extreme, so it falls in this acceptance region. Okay, so go ahead and work on the group assignments, or actually first, let me go over these examples in Excel. Okay, so on the new functions page, we have the new functions and a single new equation. So this t.inv.two-tailed is used to find the critical value for a two-tailed test. The other version, the t.inv, was on the previous week's tab, so it wasn't included here for the new functions. In this one, you just type in alpha and the degrees of freedom instead of 1 minus alpha over 2. And then you'll see that we have a couple versions of this t.dist function for different questions. The RT is for right-tailed problems, 2t is for two-tailed problems, and the t.dist, just the regular one, is for left-tailed problems. And they give you the p-value underneath the curve to the right of the critical values. For the t.dist left-tailed version, you have to include this extra argument of true, and this gives us the cumulative probability to the left, which is what we want. For equations, we have this t-calc is equal to x bar minus mu naught divided by the standard error, and it's the equation for calculating t-calc. Okay, so for our two-tailed t-test, we have our soil pHs. First thing I'm going to do is actually fill in the hypotheses. So our hypothesis is that our x bar, our sample mean, is equal to 6.3. It is equal to the population pH. Our alternative then is that our x bar is not equal to 6.3. It's something else. Putting that into English, our biological terms, excuse me, would be that the average soil pH, is equal to 6.3. The alternative is that the average soil pH is not equal to 6.3. So our sample size is equal to the number of samples we've taken. Our mean we calculate using average. Our standard deviation is calculated using the sample version for standard deviation. Our standard error is equal to our standard deviation divided by the square root of our sample size. Our degrees of freedom is our sample size minus 1. Our null mean is 6.3. We were given that in the word problem. And now we can calculate our t-crit using the t.inv two-tail. This is a two-tailed test. We're going to do 0.05 because that is our alpha value, the value that we're trying to beat with our p-score, our p-value, and then our degrees of freedom. We can also look that up on the table like we did before. So if we go to 15 degrees of freedom and our alpha value of 0.025, because we're splitting the alpha between the two tails, we get 2.1, sorry. Am I looking at the right one? Oh, wrong degrees of freedom, that's why. 19 degrees of freedom, alpha is 0.025, we get 2.093. So that is right. That's a good way to double check that you are calculating your values correctly. And remember that this two-tailed version knows that we're splitting this alpha value. That's why we don't have to type it in as divided by 2. Two-tailed, the 2t, tells Excel to split the alpha. Our t-calc is equal to our sample mean minus our null mean divided by our standard error. And then we calculate our p-value using the t.dist two-tailed version with our calculated value, our t-calc, and our degrees of freedom. And there we go. I also really recommend that you draw this out on a piece of paper. So we've got our t-crit for the two-tailed test as negative 2.093 and positive 2.093. Our t-calc is 3.18, so it's way over here. So just looking at that, we would reject our null hypothesis, but looking at our p-value, which is 0.00487, so way smaller than 0.05, we would also reject the null hypothesis because we reject when p is less than alpha. So we would write that in the conclusion. So we reject the null hypothesis. We could say p is less than 0.05. But then I also want you to explain what that means. The pH of the soil after adding fertilizer is not equal to 6.3. For the second example, our null hypothesis is that our sample mean is equal to or greater than 1.0. The alternative is then that our X bar is less than 1.0. That would be if our new protein is an enzyme, the molarity of the solution would decrease, the concentration would decrease. We put that into words, we'd say the average molarity is equal to or greater than 1. Our alternative would be that the average molarity is less than 1 molar. Our sample size, we can calculate with count. Our mean using average. And if you've ever wondered how I go through these functions so fast, I just use the keyboard. I do equals, and then you can use your arrow keys on your keyboard to actually scroll through these. It's way faster. When you highlight the one you want, you just hit tab. It's way faster than using your mouse to like click everything. Our standard error is our standard deviation divided by the square root of our sample size. Degrees of freedom is our sample size minus 1. Our null mean is 1. Our t-crit we get using t.inv. We're not going to use two-tailed this time because it's not a two-tailed test, it's a one-tailed test. And we're trying to see if our value is less than the other value. This is a left-tailed test. So there's a couple options here. For probability, we can actually just type 0.05, the entire alpha value, and our degrees of freedom. And that will give us a negative t-value. We could also do the negative version of t.inv and put the positive alpha value, the 1 minus alpha, which would be 0.95, and then our degrees of freedom. And that will give us the same negative value. Again, the reason for that is if we think about this being a number line, from 0 to 1 in terms of alpha values, this value would be 0.05 and this would be 0.95. Then if we kind of overlay our t-distribution on top of that with our mean of 0 here, this would then be a positive, this entire side would be positive and this entire side would be negative. So when we type in this 0.05, it gives us our negative t-crit. When we type in the 0.95, it gives us our positive t-crit. So make sure to keep that in mind. This is a left-tailed question, so our t-crit value should absolutely be negative. If it's positive, that means that we're looking at the positive side, which we don't want to do. Our t-calc is our mean minus our null mean divided by our standard error. Just looking at that, we can already see that our calculated value is less extreme than our critical value. It is closer to 0, closer to the mean, the center, than the critical value. That'd be like right here. If these are the rejection zones. In this case, this isn't a rejection zone because it is a left-tailed test, so it's just over there. We can then calculate our p-value, which we should already expect to be greater than 0.05 because our t-calc is in the acceptance region. So if our t-value or p-value is less than 0.05, then we should probably double check something. We're using the t.dist because this is for the left tail, and it tells you to. If you highlight it, it says returns the left-tailed student's t-distribution, and that's what we want. Click our calc, our degrees of freedom, and this version requires that we write true at the end. And we do. We get a value, our p-value is greater than 0.05. So the conclusion that we come to is that we accept the null hypothesis. Our p-value is greater than 0.05. You could also say t-calc is greater than, I guess, t-grid, or t-calc is less extreme than t-crit. any of those. In biological terms, that would mean the tested protein did not decrease the molarity of the solution. Therefore, it is probably not an enzyme. Okay. So go ahead and work on these group work examples, and then we will go over them in a second. Okay, so for question 1 on page 114, a sample of 36 mice, that's our sample size, was given growth hormones to see if it would affect the mass at 6 weeks. The mean mass for individuals in the sample was 26.5. So that's our X bar, 26.5, with our standard deviation of 4. Is there any reason to doubt that the true mass under this hormone treatment diet is equal to 25? So that's our null mean. That's what we're asking about. The standard mass of 6 weeks for laboratory mice. Okay, and alpha is 0.05. So first off, our null hypothesis is that our X bar is equal to 25 grams. And our alternative is that X bar is not equal to 25 grams. Putting that into words, that'd be the average mass of mice is equal to 25 grams. The average mass of mice is not equal to 25 grams would be the alternative. Okay, so let's fill out the rest of this and solve to see if there actually is a difference between the two. Standard error is our standard deviation divided by square root of the sample size. Our degrees of freedom is our sample size minus 1. Our critical value we get using t.inv two-tailed. This is a two-tailed question. The probability is 0.05, so alpha is 0.05. Our degrees of freedom is 35. Our t-calc is our mean minus our null mean divided by the standard error. So our t-calc already looks more extreme than our t-crit, so we're probably going to get a low p-value. So we enter our t-calc and our degrees of freedom. And we do, we get a p-value less than 0.05. And again, I really recommend you draw these out. So our t-calc, or our t-crit was 2.030. And technically there's 2, right? Because this is a two-tailed test, it's technically plus and minus 2.030. Our calc value is 2.25. So it falls into the rejection zone, which matches with our p-value of less than 0.05. So we reject the null hypothesis. P is less than 0.05. Our t-calc is more extreme than t-crit. The mass of mice after 6 weeks is different, is significantly different from 25 grams. For question 3, So an ecologist is studying the bamboo that grows in a region that has phosphorus-rich soil. Other studies and other plants suggest the bamboo will be larger because of this. He has data from reputable sources that gives the mean diameter at breast height of bamboo as 125 centimeters. So that's what we're comparing to. That's our null mean, 125 centimeters. He measures 12 bamboo plants, so that's our sample size, and obtains a mean of 129. That's our X bar, with a standard deviation of 5.784. Does it appear that the bamboo plants in this region are unusually large? So this is a right-tailed test. So our null hypothesis is that our X bar is less than or equal to this 125. And our alternative is that our X bar is greater than this 125 centimeters. So the mean diameter of bamboo is less than or equal to 125 centimeters. The alternative is that the mean diameter of bamboo is greater than 125 centimeters. Okay, so our standard error is calculated by dividing our standard deviation by the square root of the sample size, degrees of freedom, sample size minus 1. Our t-crit is t.inv, not two-tailed this time, just the .inv. This is right-tailed, so I'm going to use the 0.95 so that I get the positive critical value for an alpha of 0.05. Select our degrees of freedom. Calculate our t-calc, so our X bar minus the null mean divided by our standard error. We can see that our t-calc is greater than our t-crit. So our t-crit is 1.795 or 96 technically, and our calculated value is over here. It's 2.396. So just looking at that, I expect to find a p-value that is less than 0.05 because our calculated value is more extreme than our critical value. So t.dist right tail, our calculated value, and our degrees of freedom. And we do. We have a p-value that is less than 0.05. So we reject the null. P is less than 0.05. T-calc is more extreme than t-crit. The average diameter of bamboo in this region is greater than 125 centimeters. Question 4, a drug researcher has developed a drug that she hopes will reduce cholesterol levels. She only cares about whether it lowers the levels since increasing the levels is not the goal of such a drug. So we're looking at the left tail. Let's see, she has a set of long-term volunteers that have their cholesterol levels checked often, and the mean total cholesterol level of this group is known to be stable at 200 micrograms per deciliter. Let's see. So that is our null mean, 200. She administers the drug to 15 patrons. That's our sample size, and obtains a sample mean of 196. with a standard deviation of 9.769. Okay. So we want to know if this drug decreases cholesterol. So X bar is greater than or equal to would be the alternative, or sorry, the null hypothesis of 200 micrograms per deciliter. The alternative is that our X bar is less than 200 micrograms per deciliter. In English, that would be the average cholesterol level is greater than or equal to 200 micrograms per deciliter. The alternative would be that the average cholesterol level is less than 200 micrograms per deciliter. So solve for our standard error, our degrees of freedom, and our critical value. We're going to use the 0.05 instead of 0.95 because we want the negative critical value. T-calc is X bar minus the mean, the null mean, divided by the standard error. Looking at this, our calculated value is less extreme than our critical value. Our critical is negative 1.761, but our calc is actually not as negative, not as extreme, negative 1.586. So it falls in the acceptance region. So I expect our p-value will be greater than 0.05. And it is. So we accept the null hypothesis. P is greater than 0.05. T-calc is less extreme than T-crit. The drug does not reduce cholesterol. And finally, for question 5, the mean weight of adult male robins is accepted to be 42 grams. So that's our null mean. It has been proposed that females may differ in size. The body weight values below were collected for a set of 16 female robins. Do these data values suggest that females have adult weights that differ from males? So, do they differ? This is a two-tailed test. So X bar is equal to 42. X bar is not equal to 42. See, males and females have the same, well, I guess I'll write it the same way I have the others. The average weight of females is equal to 42. The average weight of females is not equal to 42. Okay, so the other problems gave you all of the X bar and the standard deviation. In this case, you have to calculate them yourself. So we're going to use average and standard deviation for the sample, so dot S. Standard error, going to calculate that. Calculate the degrees of freedom. Our critical value is equal to T dot INV, two-tailed. Our probability is 0.05. Our degrees of freedom is covered up, but I know it's 15. Our t-calc is our sample mean, which if you just look at it is 42.25, not very far off from 42. So expecting that we're going to have some pretty similar, pretty small values. Yeah, that is 0.35 standard deviation units from the mean. And much, much less extreme than our critical value. So our p-value should be pretty big. Oh, not right-tailed. I meant to do two-tailed. And it is 0.72859. So that's saying that there is a like 73% chance that we would get this mean, this 42.25, if the population mean really is 42. So let's calculate a confidence interval for this as well, and then we can kind of get an idea of what an extreme value might actually look like. So this is our mean plus our critical value times our standard error. And this would be our mean minus our critical value times our standard error. Written out the way that it would be normally would be this, and so between these numbers, so if we got a mean value outside of these bounds, we might have cause to believe that the mean weights are actually different from each other. But as it is, we can come to the conclusion that we accept the null hypothesis. P is greater than 0.05. T-calc is less extreme than T-crit. Males and females weigh the same. And that's it.